Okay, so now comes the second part of lecture 3. It is about endemic models. So some diseases remain in the community for a long period of time. Many of these, the so-called childhood diseases do. Mumps, rubella, chickenpox, measles used to be, but now there is a vaccine which makes it not very common in Sweden, and so on. I guess influenza to some extent also stays in the population. However, it leaves Sweden and goes to other parts. In our summer, it is present in other parts of the world, and then it comes back to Sweden in the next winter. So that's a slightly different story. But and also for many animal diseases are endemic. So now I will try to talk a little bit about this. So when we want to make some mathematical models for a long-term situation, different from a short-term outbreak, it's unrealistic to assume that we have a fixed population. So then you have to allow that people die and new individuals are born. So here comes a low math level for such models. So we consider an SIR, infectious disease. So people are susceptible at birth. Sometime in life they might get infected. They are infectious for a period of time and then they recover, and we assume that you have lifelong immunity. So think of childhood diseases: mumps, rubella, chickenpox, measles, and several others. So that is the model, the disease type we consider, and then let's assume also that we have a population at equilibrium. So what I will say now is not applicable to a population which grows at very high speed or that declines at very high speed, or if the disease just arrived to the community. So for instance, probably COVID-19 might become endemic later on, but right now it's not. So it would not be applicable to COVID-19 now. And suppose that the disease is endemic, so it is constantly present in the community. And let's assume, here I guess it's a little unrealistic things, because nearly all infectious diseases have big seasonal fluctuations, but let's forget about them here. So we have an endemic disease that is present in the community and it is at some equilibrium state. And we let S tilde denote the fraction of susceptibles at this equilibrium state. I tilde is the fraction, the community fraction that currently carry the disease. And R tilde is the fraction that are currently immune to the disease. And as before, we let R0 denote the average number of infections caused by one individual, assuming that everyone was susceptible. So at equilibrium, everyone will not be susceptible, but R0 is defined for the situation that everyone is susceptible. So think of childhood diseases. So if we are at some endemic equilibrium, how many new people does one infected person infect? If you think a little bit about this, you realize that the answer must be 1. Because if the answer was, let's say, 2 or something bigger than 1, the number of infected people would increase, so we would not be in equilibrium. Similarly, if the number of people you infected was on average 0.5, then the number of infectious would be on decline, so you would not have an equilibrium. So at equilibrium, more or less by definition, each infected person infects on average 1 new person before they recover. Okay, so that is clear. But then thinking of the model, how many people do you on average infect at equilibrium? if there was if everyone was susceptible, the answer is R0. But now everyone is not susceptible, so the average number of people you infect is then R0 multiplied by the fraction of the community that is susceptible. So here is the number of people that you infect on average at equilibrium. Suppose, for instance, that only 30% are susceptible to the disease, so most people have had the disease, and suppose R0 is well, suppose 20%, yeah, so, and then R0 is 3, and then the number of people you infect is R0 times the fraction that is susceptible. So we have concluded that it must equal to 1, but also from the model it must equal to R0 times S tilde. So we have this equation, which means if you solve for S tilde, you have that S tilde must equal to 1 upon R0. So this is rather magic to me. If you know what R0 is, you will be able to say what fraction of the community that is susceptible to the disease at the endemic equilibrium. So if R0 is 10, S tilde is 10%, or 0.1. Another way of thinking of S tilde is in terms of the duration of your life. If you are born susceptible, and then you get infected at some time in life, then you're infectious for a short period of time, and then you're immune for the rest of your life. So the amount of time you spend of your life that you spend susceptible is the number of years before getting infected divided by the total life length of yourself. So another way of saying what S tilde is that it should equal the average age at infection divided by the average life length. So this can be used if you are a statistician. Suppose you want to know what R0 is for an endemic disease, then you call Karolinska Institute and find out at what age do people typically get infected by this disease. And then you call Statistics Sweden, or you look up in Statistics Sweden yearbook what is the average life length in Sweden. And from that you compute what fraction are susceptible, and then you rewrite this equation by saying that R0 should equal to 1 upon S tilde. So if you know S tilde, it means you know what R0 is. So you would estimate R0 by knowing at what age people get infected and how long they live. So these two exercises are related to this observation. You can do the same thing, the same type of reasoning as we did here for susceptible, you can do that for infectious. So suppose that you are infectious on average iota, this is the Greek letter iota, so it's a corresponding thing to I. So if iota is the average length of the infectious period, and L is the average life length, then iota upon L is the average time of your life that you are infectious. And since the population is at equilibrium, the fraction of the community that are infectious will be equal to this average duration of the infectious period divided by the average length, life length. So I tilde will equal to this. So here are 3 sets of exercises relating to that relation. So put some numbers into this equation. Suppose you live for 75 years and that your life, the infectious period is 1 week. Compute the average fraction infected. And then you, this was the average fraction, and then you look how about the average number infected, and you do this for 2 different communities, Iceland and England. And then you should think a little bit about what you think will happen in the two countries with this endemic disease. And we can come back to that at the lecture. Okay, that was the end of this short second part of lecture 3. So I will now stop recording.